Global Navigation Satellite Systems is a general concept used to identify systems that allow user positioning based on a constellation of satellites. A specific GNSS are the well-known American GPS, the Russian GLONASS, or the forthcoming European Galileo and Chinese Compass Beidou. The landscape of GNSS is going to change rapidly in the following years with the modernization of GPS and GLONASS and the advent of Galileo and Compass. A number of new signals will be readily available for navigation, providing means to determine position and time with an unforeseen degree of performance. Nevertheless, the multi-constellation, multi-frequency approach poses several technological challenges. In that sense, the flexibility provided by software-defined radio approach, and specifically the GNU Radio framework, appears as an ideal environment for rapid prototyping and testing of new receiver architecture. In GNSS-SDR, we propose the implementation of an open-source GNSS software receiver freely available under the general public license. This project provides a common platform for GNSS signal processing and data gathering for scientific applications, testing of algorithms, receiver design, and educational purposes. This tool is intended to foster collaboration, increase awareness, and reduce development costs in the field of GNSS receiver design and customized use of GNSS signals. GNSS-SDR is an open-source C++ project based on the GNU Radio framework that implements a generic architecture of a GNSS software-defined receiver and already provides a working implementation of a full processing chain of a GPS L1CA receiver, from the output of a radio frequency front end to the computation of position, velocity, and time. The proposed receiver provides an interface to different suitable radio frequency front ends and implements all the receiver chain up to the navigation solution. Its design allows any kind of customization, including interchangeability of signal sources, signal processing algorithms, interoperability with other systems, output formats including KML, RINEX, and NMEA, and offers interfaces to all intermediate signals, parameters, and variables. The software allows an arbitrary number of different algorithms and implementations for each required processing block functionality, allowing the definition of completely customized receiver flow graph by choosing one of the existing alternatives for each block. This modular nature of the receiver allows the definition of clearly specified scope activities such as development of interfaces to different front ends, new synchronization algorithms, interfaces to other sources of information, a multi-frequency, multi-constellation approach, the addition of new cool features, etc. Suggests a test-driven development approach. This methodology is claimed to offer valuable benefits to software development. It facilitates change, simplifies integration, automizes documentation. It helps to separate the interface from the implementation, increases developers' productivity, and plays a central role in the software quality assurance process. For unit testing, we found the Google C++ testing framework, also known as GTest, useful and lightweight. The acquisition detection is implemented according to a constant false alarm rate algorithm with small modifications. This algorithm performs a grid search of the test statistics for the Doppler and code delay in both frequency and time domains, which is referred to as generalized likelihood ratio test. This full search is also known as parallel code phase search algorithm. The implementation is fully configurable, allowing to acquire 4 different signal types by means of setting E1B or E1C, as well as the choice of SynBlock or composite block modulation. Signal tracking implementation consists of a delay lock loop as a code tracking loop, which is coupled to a phase lock loop that tracks the carrier phase. The characteristics of the block modulation require the use of 2 extra very early and very late correlators. This discriminator is known as very early minus late discriminator and makes use of 5 correlators.
During the Google Summer of Code 2012, we have developed more than 40 tests for most of the GNSS-SDR blocks. To execute this test, after compiling the software, go to the install directory and write run test.
In order to perform experiments with real signal, we have captured samples with a Novatel active antenna, a DBSRX daughter board, the USRP version 1, and a personal computer.
Any GNSS-SDR user can reproduce the test conducted during the Google Summer of Code and check the results for himself. To reproduce this, we should open the test of the acquisition that is in the directory source test GNSS block. On line 111 of the code, we must change the acquisition.dump property from false to true and save the changes. After that, we must compile the code. Go to the install folder and run the test. From MATLAB, go to the data folder. In this folder, we can see the data files that are written in the acquisition test. Execute the provided script plus satellite number 11 in our case. And then a plot with the results of the experiment is obtained. In order to check the performance of the tracking block within the full receiver, we must configure GNSS-SDR through the configuration file. In this file, we can see the sample frequency, the type of signal source file in our case, and where the samples file is located. number of the receiver channels, in this case 2, and how many channels will perform the acquisition process in parallel, in this case 1. The system, Galileo, the signal, 1B, and the ID of the satellites to track, 11 and 12. To run the software, go to the Install folder and run the software, including the name of the configuration file. After that, we can see the evolution of the receiver channels, going from state 0, standby, to state 1, acquiring, and finally to state 2, tracking. As soon as the channel enters in tracking mode, an estimation of the receiving power is presented on the screen at 1 second intervals. We can see that during a few seconds the tracking of satellite 11 loses lock, but after the reacquisition process it locks again with a higher C/N0. After stopping the execution of GNSS-SDR, open MATLAB and go to the Source, Utils, MATLAB folder. Open the script and set the channels variable to 2, the number of channels we have tracked. Run the script and get 2 plots, 1 for each channel. In the case of satellite 12, we can see how the tracking was locked almost from the beginning. In the case of satellite 11, we see how until 14 seconds the tracking does not lock. From that moment on, we can see that the output tracking is locked and the prompt is always above the other 4 correlators. And then the navigation bits are obtained.
As conclusions, we can say that GNSS-SDR is an open-source global navigation satellite system software-defined receiver based on GNU Radio and written in C++. Before the summer, it was able to compute position making use of GPS L1CA signals in real time. The Google Summer of Code contribution consisted of the following: more than 40 unit tests covering most of the GNSS receiver processing blocks, unit tests for validation of acquisition algorithms, validation of tracking algorithms offline, Galileo E1 signal acquisition module, Galileo E1 signal tracking module, successful acquisition and tracking of real-life Galileo E1B and E1C signals. As future work, we plan the following: the decodification of Galileo navigation message, the optimization of acquisition and tracking implementations, hybrid use of GPS and Galileo satellites in the computation of the positioning solution, and the extension to GLONASS and Compass payload. Remember that you can visit us at GNSS-SDR.org. Thank you very much for watching, and we hope that you enjoy the rest of the conference.